Good afternoon, everyone. Today we are going to study the topic AC bridges in the subject electrical measurement and instrumentation. So we'll start with the basic understanding of the subject of the topic. So basically, AC bridges. I'm suggesting AC bridges, but they could also be DC bridges. Like in the last lecture, we studied about a few of the DC bridges, which is your Wheatstone bridge and Kelvin's double bridge. Both are used for the calculation of the resistance. Let's suppose you can see here. Both are used for the DC bridges, which one is the Wheatstone bridge, the second is the Kelvin's bridge, and both are used for the calculation of the resistance. That is your DC resistance. Now, the other AC bridges could be your capacitance comparison bridge, inductance comparison bridge. This inductance comparison bridge, Maxwell's bridge, Hayes bridge, Anderson bridge, Shearing bridge, Wien bridge. So basically, what we are doing in case of the DC bridges, we are only calculating your resistance because resistance is a DC component. Whereas in case of AC bridges, you can calculate other components. You are calculating impedance. Now, impedance could be a composition of your resistance, inductance, and capacitance. There could be different compositions. Like particularly only R is there, only L is there, and only C is there, which is your own resistive only, only inductive, and purely inductive and purely capacitive. Or other than these three, there could be combination also, such as resistive inductive, resistive capacitive, resistive inductive capacitive, which is nothing but your RLC circuit. Now RLC could also be into two, whether it is series or it could be in parallel. Other than this, there could also be LC, that is your inductive capacitor. Now when LC is there, it acts as the oscillator, or it acts as at the resonance under the resonant condition. Okay, so here there are these bridges are there which are used for different calculation of different components. Suppose your Anderson bridge is used for the calculation of your for measuring your inductance. Your Anderson bridge is used for measuring inductance. Similarly, Maxwell bridge is also used for measuring inductance. Now there are two bridges under your Maxwell's bridge. The first one is your Maxwell inductance, and the second is your Maxwell inductance capacitance, which we are going to study further. So in the Maxwell inductance bridge, so we'll study further. Then I'll tell you about this. So this I've already told you. Now we are classifying the two bridges as DC bridges and AC bridges. DC bridge is basic. I've already discussed. It is used to measure resistance, whereas AC bridge is used to measure impedance, which is a combination of RL and C. It uses the DC voltage source as the excitation voltage or the input supply that you're providing. Now it uses AC voltage source or the AC voltage, or whether it could be single phase or three phase, depending upon the type of instrument. Depending upon the type of supply, you can use the type of instrument. Suppose it is a single phase AC supply, you can use single phase AC. Otherwise, it is three phase, then you can use three bridges. Okay. Now, this is the inductance capacitance bridge. So, like any other bridge, like or suppose Wheatstone bridge, we are going to follow the same procedure here. Like there also we had one, two, three component terms. The other one was a detector, and next is your AC supply. Because these are AC bridges, supply would be AC, like I've already told you. Detector would be a null type detector or null indicator. So whenever the current flowing through this is zero or no current is flowing through the detector, that means it is deflecting towards the center zero. Now it is a center, pointer is pointed towards the center aligned at zero. Now towards the left and towards the right, some readings are there, some ratings are there, some measuring parameters are there. Okay. So whenever it points towards the zero, that means the current across this is zero. Across the detector is zero. So that condition is basically called to be as the balance condition, like you've already discussed. So under the balance condition, R1 into this impedance, or the impedance of this first branch and the impedance of this branch, would be equal to Z2 and impedance Z3. Like we can see here, Z1 is nothing but your R1, Z2 is nothing but your R2, Z3 is nothing but the composition of R1 and L1, which will make R3 plus J X L3, and Zx or Z4 would be equal to Rx plus Jx4. So from the balance condition we have already discussed, Z1 into Z4 will be equal to Z2 into Z3. Opposites would be there. So this would, on further calculation, we are going to get the value of Rx, that is the unknown resistance and the unknown impedance. Now the unknown impedance and unknown resistance, reactance or inductance. inductance basically. So L is inductance. So unknown resistance would be calculated in terms of the known or the standard resistances. That is your R2, R3 by R1. Whereas your unknown inductance would be in terms of your standard inductance, which is known to us. So R2 by R1 would remain the same. Instead of R3, L3 would come. So here the R2 is selected as the inductive balance control. Inductive balance control means R2 is used for the balancing of your inductor. R2 is related to your inductor. And R3 is selected as the resistive balance control. R3 here is selected as for the balancing of your resistor because this is there. Now coming to the next composition, that is your Maxwell bridge. Now Maxwell bridge I've already discussed. Maxwell bridge could be Maxwell inductance or it could be Maxwell inductance capacitance. Now the what is the difference between the two? The difference would be the arms, that four arms that are there, the composition, the components that would be there would be different. Like in case of Maxwell inductance bridge, it is AD is having R1, AB is having R2, BC is having RL, and DC is having RL again. Whereas in case of Maxwell inductance capacitance, there would be a presence of capacitance also. This was R in case of Maxwell inductance, this was also R. Now in case of Maxwell inductance capacitance, a capacitor is connected here. And here R1 is there similar, remaining this is also same. Now this becomes your R3. No inductance branches there. So when we do this, we can calculate your phasor diagram. How we'll calculate your phasor diagram? Now we'll take your V as the supply voltage and lagging current I3 from it. Lagging current I3 from it. Now I1 is equal to your I3, and sorry, I1 is equals to your I2, and I3 is equals to your I4. I4 is equals to your I3. I1 is equals to I2, I4 is equals to I3. Correct? Now V is here, lagging current I3, I1 is there. So I1 is nothing but I2 only. So when in the direction of I1 and I2, I1 R2, I1 R1 and will be the same as compared to your I2 R2, right? So this is in the same direction of R1, I1, sorry. Now when you're adding, now in this case, a small capacitive resistance R is also present. That is internal resistance of your inductor, right? Of this inductor. This inductor is having this inductor is having some internal resistance which is nothing but a small r. So R3 total equivalent R would become R3 plus small r. So this into I3 would equal to your I4 into Rx, right? So this of both of them are the in the direction of your I, right? Now when you take the L component of these, isme when you are taking the L component, that is I3 into omega L, this is going to give your V3 phasor sum of both the components. This component and this component is going to give V3, right? I2, I4, all these currents are in this direction. So equivalent of this would give you V, which is your summation. So this is on evaluating, you are going to get the value of LX and RX. LX is just the same as it was in the earlier case. RX would become different because here presence of the small internal impedance resistance of your inductor L3 would also come. This is the difference. Now coming to the Maxwell inductance bridge, I already told you the difference between the two. These are the unknown parameters. Okay. So on calculating further, we are going to get this value. There it was in that case, Lx was equals to in terms of L3. Here it will come in terms of C1. Okay. Because C1 is the only capacitance that is present in the circuit. So today we discussed two, three, three bridges we discussed. Basically around three, four bridges we discussed. In the next lecture tomorrow, we will discuss about the Anderson's bridge, Hayes bridge, and sharing bridge. So stay tuned for tomorrow. Thank you.